This is part 2 of the 8.4 notes. So we're talking about tangent lines in this lesson. One thing I want to point out is that a polygon is circumscribed about a circle. So remember our polygon. So in this case, this is 1, 2, 3, 4, 5. I have a pentagon here. So the pentagon, I have a pentagon, and then the circle is inside of this pentagon. Okay. Now what's cool about this is when this happens, these lines are tangent to the circle. If I can trace the circle correctly. So I have 5 points of tangency here. So if I were to draw a radius to any of these points, this is going to be a 90-degree angle. So the polygon, when the polygon's on the outside, we say the polygon is circumscribed about the circle. If we want to reference the circle first, the circle is inscribed the polygon because it's inside the polygon. So we have a theorem with this. Our theorem states if two segments from the same exterior point are tangent to a circle, then they are congruent to each other. So I have this circle. Okay, and then it's saying if you have some point, and then kind of draw these lines from that point, and make it so that it's tangent to the circle, then the length from the point of tangency to the outside point has to be the same. So whatever that is the same as that. And then if you want to go through and read through this proof as to why it is, it's actually kind of cool. So using what we learned from the last theorem is if these lines are tangent to the circle and they meet at this point, that means that the lengths have to be equivalent. And it says assume that all lines that appear to be tangent are tangent. So they are tangent, they meet at the point, these lengths have to be the same. So I have this x squared minus 3 has to be the same length as 13. They have to equal each other. So in this one, I'm going to add 3 to both sides because that's going to undo the minus 3 here. And I get x squared is equal to 16. And then I take the square root to undo the squared. And the square root of 16 is plus or minus 4. Now my calculator is only going to tell me the positive 4, but I have to recognize that if I take negative 4 and square it, that's also going to give me 16. So if I took negative 4 and squared that, that gives me 16 as well. So I have to be smarter than the calculator. Okay, on the next one it says the 3 segments are tangent at points B, F, and D if AC is 12 centimeters. So it's talking about this entire length. CE is 20 centimeters. And FE is 13 centimeters. So pay attention to what it's talking about. FE is just this piece right here. Determine the length of AF. So I'm trying to find the length of this piece right here. Well, I love these problems. I think they're so much fun. So what I know is that this line right here and this line right here meet at an exterior point, and they're both tangent to my circle. That means if this is 13 centimeters, this is 13 centimeters. Well, if that's 13 centimeters and the whole thing is 20 centimeters, 20 minus 13 is 7. Well, now I'm back into a case like this. I have these two lines that meet at an exterior point and they're tangent to the same circle. So they have to be the same length. So that's 7. Well, if that is 7 and the whole thing is 12, this piece right here has to be 12 minus 7 is 5, which makes this side right here, because they both meet at an exterior point and are tangent to my circle, has to be 5 centimeters as well. Okay, and then one last example. So again, something similar. If this is 4, this is 4. And if the whole thing is 14, that makes 14 minus 4 is 10, which makes that piece 10 as well. And if that's 10 and the whole thing's 17, this is 7, which makes that 7. And what it's asking for is the length of RS. It didn't give me units, so that's just my answer. And we're done with the 8.4 notes on tangent lines.